So graphing radical functions. So at the end, after the last test, I said copy these 4 key concept blocks. This was one of them. We don't actually study graphing all radical functions. So really, we just do the square root and cube root. Those are the only 2 that we're responsible for. And 90% of it is about the square root. There's a little bit about the cube root, but not much. Right? So these are the shapes of those functions. So remember 2 things, right? And if you, at this point, we're not taking the square root of a negative number, right? If you put in a square root of a negative number, you get an I. And this graph, that's all real numbers, right? The x-axis is a real number axis, so is the y. So if we had I values, we wouldn't be able to graph it, not on this coordinate axis. So we have to only have x values that are greater than or equal to 0. And because we assume that the square root is the positive square root, then we can only have y values that are greater than or equal to 0. That's why it starts at 0, 0, and just goes up into the first quadrant. Right? So this is our first function, really, that we've dealt with that has a limited domain. It's not just all real numbers. Right? The domain is right here, x greater than or equal to 0. And then looking at the graph, you can see actually the y is greater than or equal to 0. Right, the cubed root function, remember, we can take the cubed root of a negative number, and the answer is negative. Right? So that's why this one does have the graph go into negative x values. And, it's got one piece in the third quadrant, one piece in the first quadrant. And, if you had to describe that shape, maybe it kind of looks like an S. Even though it looks like the graphs, maybe it's kind of like flattening out as it goes up into the first quadrant there. It is going to go up indefinitely. It's just going up slow, right? Because the y values will always be the cubed root of the x value. So it's going to be much, much less. But it does have a domain and range is all real numbers. And there's no way that'll ever change. For a cubed root function, it's always all real numbers. Okay. So whenever we start talking about parent functions, then the next thing you're going to do is transform them. Move them around, stretch them, shrink them, flip them, all those kinds of things. So that's what we're going to do now. Right? These are like the standard equations that show all the possibilities of transformations. And they're pretty similar to what we did before. Like if I compared that to absolute value, y equals a times x minus h plus k. Quadratic, y equals a times x minus h squared plus k. We always got an a, an h, and a k. For a quadratic or even an absolute value, what did the hk represent? Yeah, it's the vertex of it, right? If you're talking about a square root function, that point right there is not a vertex. It's the beginning of the graph, but it wouldn't call it a vertex. And that's what hk represents. It's the beginning point. So you can imagine that's still like probably the most important point you need to have is where does this graph start? I mean, I'm not even sure I've heard of the middle of a cubic being called the vertex, but it's probably the most important point to get right. And now these are all the things that we've done before. When you're multiplying by a constant, a, okay, if the absolute value of a is greater than 1, then it's going to stretch the graph. If the absolute value is less than 1, that means it's like between -1 and 1, then it shrinks the graph, right? If a is less than 0, it flips the graph across the x-axis. Right? Now the h is what's being subtracted from the variable inside the function. If h is greater than 0, the graph moves to the right. Okay, you know, we did this before, like with an absolute value function. Y equals x minus 2 plus 3. You know, we said when it's minus inside, it goes to the right. But if it's minus inside, that means the h is positive, right? Because the minus is part of the formula. So when h is greater than 0, it goes to the right. When h is less than 0, it goes to the left. If the k is greater than 0, it goes up. If the k is less than 0, it goes down. Okay. So, I'm not thrilled with my directions there, but graph or describe. The main point of this is we know what the shape of the graph is, right? We could get it more accurate if we plot points and get it, you know, and do that. But we should be able to kind of draw an approximate graph just by understanding the parent function and the transformations. And from that, that will be enough to know the domain and the range. And the domain and the range are the important concepts we're trying to get out of this right now. You know, there's almost no questions on the SOLs that just ask, you know, graph this radical function. The kind of questions you get are always about domain and range, or about just recognizing the shape of a graph. So let's see. In this problem, what is the value of a? A is the 2, right? That's what's multiplying. And what would be the value of the h? -1, right? That's why it says x plus 1, because it's x minus -1. X plus 1. So if I was going to graph this, so the a is telling us that we're going to stretch it, and the -1 is saying go 1 to the left. So I could just like make an approximate graph, right? I'll just say, okay, it starts here, and it goes off into the first quadrant like that. Okay, now from that picture, let me say what the domain is and what the range is. Domain. What is the domain? X is greater than or equal to -1, right? It starts right here, and that's x equals -1, so -1. And what is the range? Yeah, the range is y greater than or equal to 0. Now, I can make that graph better than that, but it won't change the domain and the range. The first point you should put in is the h. You know, we want to get the beginning of this thing right. So we're going to definitely put in -1. And then I would suggest, because we don't really want to go to decimals here, let's just like pick values that lead to square roots that are, you know, of perfect squares. So let's say, let me go one more than that, and then let me go 3. So watch what happens. When I put in -1, -1 plus 1 is 0, so this is 0. When I put in a 0, now I've got the square root of 1, which is 1, times 2 is 2. And I put in 3, 3 plus 1 is 4, the square root of 4 is 2, 2 times 2 is 4. So I'm picking these x values because remember, I get to pick the x values. And I'm picking them just so they lead to perfect squares. And that makes it a little easier to graph. Okay, now if I graph those 3 points, the first one is here, the second one 0, 2. Actually, I got that one pretty good. And then 3, 4. Okay, that would be a little bit more accurate. Of course, my drawing will probably make it bad. But by far, the thing is, you want to just get the general shape of the graph so that you understand domain and range. Okay. Okay, so let's say, in this case, A is -2, H is 3, K is 2. So that -2 is going to do what? 2 things. What are the two things that negative a equals negative 2 does to you? It flips it, and it stretches it, right? Because the absolute value of negative 2 is greater than 1. So, so I know it's going, let's see, right 3, up 2, and then it's going to be flipped, so it'll be something like this. What does that make the domain in the range? What's the domain? Domain, x values. Right, remember the x values are on this axis. Greater than or equal to 3, right? X is greater than or equal to 3. And what is the range? Right, on the y-axis, where does it start? At 2, right? And then it goes down from there. So you're going to say y is less than or equal to 2. Again, I can make this a little better. The graph could be more accurate than that. I definitely would want to start with the h value of 3, and then I'm going to put in 4 and 7, because those are going to lead to the square roots of perfect squares. Okay, so if x equals 3, the function equals 2. If x equals 4, then we got 4 minus 3 is 1. Negative 2 times 1 plus 2 is 0. And 7 minus 3 is 4. The square root is 2. Negative 2 times 2 is negative 4. Plus 2 is negative 2. So I could make this a little better graph. There's the first point. 4, 0, that's pretty good. And 7, negative 2. So that would be a better graph than the first. So try to graph that one. Okay, so what is that negative 4 telling us? Flip and stretch. Remember, if the absolute value of a is greater than 1, it's a stretch. And absolute value of negative 4 is 4, so that's a stretch. Then don't take the negative, because negative 4 is less than 1. But that just means it's stretching down. Okay, and then what about this 2? The plus 2? It's going to go up, right? So I know that the parent function looks like this, right? Something like this. So I want to take that, I want to move it up 2, and then stretch it down like that. Right, it's been flipped, so it goes the opposite direction, and it's going down faster than, because it's being multiplied times 4. Now in terms of domain and range, domain, what would you say is the domain? X is greater than or equal to 0, right? Remember, the x's are these values here, so it's starting right there and goes to the right. And what about the range? Nope. It's less than or equal to 2, right? 2 is the greatest value there, so y less than or equal to 2. Now, let's try to make that a little bit better graph, x, y. So definitely we want to start with 0, and then let's put in 1 and 4. Right? When x equals 0, y equals 2. When x equals 1, y equals negative 2. When x equals 4, then it's negative 8, negative 6. So let me put those values. That would be here, 1, negative 2. That's actually pretty good. And 4, negative 6. Not too bad. So that would have been a little more accurate if I would have gone through those points. But as bad as I do tracing this stuff anyways, actually I'm pretty happy with that. the point being that even your quick sketch, just taking into account the parent function and the transformations, is going to be close enough to get the domain in the range. The rest is just kind of a nicety, whether it's exactly there or not. Okay. So try that one. So I'm going to do it backwards. This is backwards from what I was doing. Instead of just sketching it in first, let me do the 3 points. Why am I going to start it with 3? That's the h, right? That makes 3 minus 3, 0. That's going to be the starting point of the graph. Okay, so what are the other two x values that I'm going to pick? 4 and 7. Okay, why? Because 4 minus 3 is 1, 7 minus 3 is 4. Those are perfect squares. So let's calculate. This is going to be 3, negative 1, 4, 1 half, negative 1 half, and 7 minus 3 is 4 squared is 2. That's 0. So I'll make a table of values. And 3, negative 1 is here. 4, negative 1 half is here. And 7, 0 is here. Draw the graph. Okay, now let's look at the transformations. What was the effect of the 1 half? That was a shrink. And does it look like it's been shrunk? Yeah, I mean the parent function goes up like this. So it definitely looks like it's been squashed a little bit. Okay, and what about the minus 3? Right? And the minus 1 down. And does that all look good with our graph? This graph right here? 3 to the right, 1 down, shrink. That looks good. What's the domain? Domain is x greater than or equal to 3. Range. Y is, Anna? Greater than or equal to negative 1. Right? And again, this was just comparing it to the parent function. That might be the end of the square roots. Okay, now we get to the cube roots. Again, what was the basic shape of a cube root function? Kind of like an S, right? Kind of like a flattened, elongated S. So we want to take that and move it around. Now, the middle of the S is going to be the HK. Go ahead, Mike. So again, let's see. So this A, H equals negative 4, K equals negative 1. Okay, so the HK is the middle. Negative 4, negative 1. Okay, if I make my table of values, I definitely want to have that point in there. Negative 4, negative 1. Okay, now if I want to stick to values that are going to lead to the cubed root of perfect cubes, I'm pretty limited here, right? I mean, I can definitely go to minus 5 and minus 3. If I go either side of the h, then when I do the subtract, like negative 5 plus 4 is negative 1. The cubed root of negative 1 is negative 1. Negative 1 to the third equals negative 1. 3 times negative 1, negative 3, minus 1, negative 4. Okay, if I do negative 3 plus 4, I get positive 1. The cubed root of positive 1 is positive 1. 3 times 1 minus 1 is 2. So let me graph those 3 points. Negative 5, negative 4, negative 3, positive 2. Okay, now, if I wanted to have another cubed root of a perfect cube, how far away would I have to get? What's the next perfect cube after 1? 8. So I would have to get to be 8 more, which would make a positive 4, or 8 less, which would make negative 12. And the graph background I put on there, I didn't even leave room for it, which is not good. I should have. But in any case, we need to draw it like it looks like it's an S. So I'm going to go through there. What happened there? Switch the mode. Something like that. So now, what is the domain and the range? Domain and range, all reals. It always is. Okay, let's try another one. Let's see if I missed one. Yeah, I did, didn't I? So let me go back and do this one. Okay. So let's see. What is going to be the center of this S? Positive 4, 0. Good. 4, 0. So let me go over here. 4, 0. Okay, let's make a little table of values here. So we definitely got 4, 0. What are 2 points I can add to that? So that I'm taking the cube root of a perfect cube. No. How about 3 and 5? 1 either side. Okay, 3 minus 4, negative 1. 2 times negative 1, negative 2. 5. 5 minus 4 is 1. Cube root is 1. Positive 2. Okay, let me put those on there. 3, negative 2. 3, negative 2, sorry. And 5, positive 2. Okay, then how far would it have to go to get a cube root of a perfect cube? I would either go 8 to the right, which is going to be like off my slide. If I go 8 to the left, where does that leave me? Negative 4. That actually is pretty close. It is a little bit off the graph. But I can see it. It goes something like this. And domain and range, all real numbers. Okay. 10, 11. So try to graph that one. If you just plot those 3 points, you could connect them with a straight line, right? But that wouldn't show you understand the shape of a cube root function. So make sure you don't do that. Right? And now this one I can almost get to 8. 8 is like right over here. Right? If I did 8, then I would get the cube root of 8 is 3 is 2, is minus 5 is negative 3, and put in negative 8, I'll get negative 2, negative 7. So it's about right there and there. And that will look like an S. A fancy R for all real numbers. And I think there's one more. And then we're done. Okay, what's the minus sound you do? Flip. And how about the plus 2? No. Left 2. And the minus 3? Down. So left 2, down 3, and flipped. So in approximate terms, it's that. Now, if I plotted points, it would be like 1 right there, 1 right there. And let's see, minus 2 plus 6 would be right there. And this would be off, it would be off the chart over here, but that's pretty close to where it would look like. And domain and range again, all real numbers. Okay, and just one more thing I'm going to show you. So, y equals negative the square root of x. Okay. So we know that the positive square root of x goes like this, and the negative square root of x should go where? It should go like that. But in fact, you can also flip it across the y-axis. And the way you flip it across the y-axis is you go like this. The square root of negative x. Right? You put the negative inside. They don't have this in the book. You're not going to run into any problems. But it's an obvious question. You know, well, how do you do that kind of a flip? And it makes sense because here's the graph. So now you can plug in negative values for x, but you can't plug in positive values of x. When you put in a negative value of x, then the negative in front of it makes it positive, and now you can take the square root. That's why the graph goes to the left, right? And it's still positive because we assume that that's a positive right there. Now, when we did absolute value, y equals the absolute value of x, right? We know that that was a v that looks like this. So what would happen if I flipped that one across the y-axis? It would be the same v, right? Because it's symmetric with respect to the y-axis. It would just look like it stayed in place. So I mean, you really can't show that kind of transformation until you get to the square root, and then you can see it. Okay. So that is the lesson. That's the whole unit. That's the homework.